In this video, we'll discuss special speedup techniques for architectural hyperparameters that are studied in the field of neural architecture search. Let's dive right in. Special techniques for optimizing architectural hyperparameters. I would like to start this video by relating the field of neural architecture search, short NAS, to the field of hyperparameter optimization, short HPO, that we've been discussing throughout this lecture. So neural architecture search aims to automatically optimize architectural choices, just like hyperparameter optimization optimizes any type of choices. And while since the architectural choices are choices that HPO can tackle, NAS is actually a special case of HPO. And all of the methods, therefore, that we discussed for HPO actually apply for NAS directly. So anything from multi-fidelity optimization, prior-based optimization, so we could have priors over neural architectures. We could do transfer learning across neural architectures, etc. But what makes NAS special is that there are special speedup techniques that only apply to architectural hyperparameters. So for example, you can share weights of different neural architectures, and you can inherit weights from one neural architecture to another one. And these concepts just wouldn't apply like that to the space of hyperparameters. And because neural architectures are so important for deep learning, NAS is actually very heavily researched in the deep learning community. And there are over 2,000 papers that address neural architecture search. And despite the fact that NAS is the subset of HPO in terms of the problem formulation, there are all these special speedup techniques for NAS, and that makes NAS a much more heavily researched field than the rest of HPO. HPO is important, but it's sort of seen to many people as a nuisance problem, whereas coming up with a neural architecture, that is something that a lot of deep learners care about. The first type of speedup technique for neural architecture search I would like to discuss is the sharing of weights in a so-called one-shot model, or also called a supernetwork. So a supernet, visualized here, is a hypergraph in which there are multiple edges going from one node to another node, and each of these edges denotes one of a possible set of operations. And the nodes in this graph denote sort of latent states, tensors. And the operation candidates, they just tell us what happens in between these tensors. So you could have, for example, operations like 3x3 convolutions or 5x5 convolutions, etc. And then each of the possible architectures is going to be a subnetwork of the supernetwork. And the weights are shared between the different architectures. So for each of these operation candidates, there is going to be a tensor of weights, and that is going to be the same for all of the architectures that actually have this particular edge. And this then allows us to only train a single model, the supernet, and thereby drastically reduce the search costs. Basically, we train a single model and we just evaluate a path in this model. A very popular algorithm that exploits the sharing of weights in a one-shot model is the so-called DARTS algorithm. DARTS stands for Differentiable Architecture Search. And what it does is it uses a one-shot model, and then in the one-shot model, for each of the operators, it associates with it a continuous architectural weight alpha. So in this image here, again, we have node 0 and node 1, and there's 3 operators connecting the node. So there's 3 edges, the red, the blue, and the green edge going from 0 to 1. And each of them stands for an operator, and each of them is associated with an architectural weight alpha. And these alphas are then actually optimized to start from the uniform distribution and in the end actually give more weight to some of the operators than to others. What happens with these weights in the end? So how do you compute the latent states in a node given the latent state in the node before? So basically, each of these operators acts on the latent state and gives you a new latent state. And the alphas are simply giving you weights for the outputs of the respective operators. And this is nothing else than a softmax. And you do that, so you compute the result of each of the operators and you multiply it with its softmax weight, and then you sum over that. And if you have multiple incoming edges, here is this node 2, then you sum over the edges that come from the various preceding nodes. All right, so the cool thing is that these alphas, they're actually continuous, and so we can actually optimize them with gradient descent. So we can use gradient descent to optimize over this discrete set of different architectures. Now, of course, gradient descent will not yield something that is discretized, but it gives us these different weights that are continuous. And in the end, we actually want a discretized architecture because, well, we don't want to have this very large architecture that has to store, that has to actually compute all of these operators going from node 0 to node 1, but we rather want a discretized architecture. And so for that, basically, in a rough approximation, DARTS takes the maximum of each of the alphas for each of the connections. How does DARTS do this optimization? So going from the uniform distribution to the optimized distribution, well, that is a bi-level optimization problem. So it's trying to find the alpha such that the optimized weights for alpha, optimized with respect to the training loss, actually, when you use these optimized weights, then you get the minimum validation loss. So standard bi-level optimization, just like for gradient-based hyperparameter optimization. And this, like for gradient-based hyperparameter optimization, can be used by alternating SGD, alternating between the architectural parameters and the weights. So in a nutshell, in the first order DARTS algorithm, you simply update your one-shot weights, so the weights of this one-shot model, by doing a gradient step on the training loss, and then you update the architectural parameters alpha by doing a gradient step on the validation loss. And then in the end, you return the argmax for each edge in order to return a discretized architecture. So note again the similarity to gradient-based HPO here. It's the same type of alternating SGD algorithm that we saw there. And like there, we actually don't have a guarantee that this alternating SGD actually converges. However, in practice, this optimization is actually not so much the problem in DARTS. That tends to work quite well. But there is a bigger problem in this final discretization. And there are also problems in the size of the one-shot model that just requires quite a bit of memory. So if your one-shot model is much larger than the final architectures that you want to search, then that makes it problematic to actually really find some architecture that you want to use in the end. And one solution for that problem is weight entanglement. Now this weight entanglement, that actually reduces the memory cost of the supernet by reusing weights. Reusing weights not only between architectures that share the same operation in the supernet, so that we saw before, different architectures that would share an edge also share the weights of that edge. But here in weight entanglement, you also share weights between operations. I think this is easiest to understand using an image here. So in this image here, we have actually the entangled weights of 3 different operators, a 7x7 convolution, a 5x5 convolution, and a 3x3 convolution. And all of these are just represented in these 49 different weights. So this is the 7x7 convolution, and there's a 5x5 convolution. That's the inner 5x5 weights, and there's a 3x3 convolution. And all of these weights are just shared between each other. And the final operation then can also be computed by only touching each of these weights once. So these outer weights here, they're just being multiplied by this alpha 1. The weights in here, they're multiplied by this alpha 2 and alpha 1. And the innermost weights, they're multiplied with alpha 1, alpha 2, and alpha 3. So in this case here, the largest subnetwork is the one where you actually apply a 7x7 convolution, and the computational complexity of this largest subnetwork in terms of both memory and time is actually the same as the one of the supernet, because, well, we need to store the 7x7 matrix here, and the computation also touches each of the elements of the 7x7 matrix once. So the nice thing about this weight entanglement is that this doesn't just work for entangling the weights of convolutions of different sizes, but you can also entangle the weights of architectures of different depth or width. So for example, if you have an architecture that is 2 layers deep and one that is 3 layers deep, then the weights of the 2-layer architecture can be also the weights of the first 2 layers of the 3-layer architecture, and you can share those weights. Likewise, in terms of widths, if you have transformers of different embedding sizes, then the prefix of the large embedding size could just be the embedding of the lower size. So you can actually search over the depth and the width of these neural networks, and also sizes of the convolutions, all in a weight entangled space. And in this weight entangled space, the largest sub-architecture is actually identical to the supernet. So the computational complexity of operating in these architectures can then actually be relatively small, and we really have a chance of finding architectures that are sort of the largest we can possibly fit into our memory. We can directly find these with neural architecture search, where previously we could only find architectures that are quite a bit smaller than our maximum memory size. Another nice thing that we can do in architectural search spaces, and not in general hyperparameter optimization, is to inherit the weights from one network to another. So when you, for example, locally expand a network by adding a layer, then we can simply inherit the weights of the unchanged part and not retrain them from scratch, but just save that computation. And that actually can be done by introducing a so-called network morphism. So network morphisms are operators that change the network structure, but not the model function. So that means for every input to the neural network, you get exactly the same output as before, but you have a different architecture. And one way of doing that, for example, by adding a layer, well, you do need to make sure that you initialize the weights of that layer correctly, such that you actually get a network morphism like that. So in this case here, for example, you have an original model and you want to add a layer to this, then in this particular case, you just initialize this as an identity mapping, and then this deeper model here actually computes exactly the same function as this original model here. And if this original model is already trained really well and you just want to now train a model that is a little bit deeper, then you can warm start that from this model here that has already trained a large part of the network really well. And you could then, for example, first train the blue weights a little bit and then train all the weights a bit more, or fine tune all of them directly. And that typically allows you to get better performance relatively quickly. And these network morphisms then actually can also be used in order to do a relatively fast local search through the architecture space. And there has been some work on actually training, for example, large transformers by first training smaller transformers and then expanding them over time. And there is some evidence that this can actually be just as fast as training the large transformer. And it has additional nice properties, such as, well, getting you relatively quickly an idea where the performance is headed, and then you can also do multi-fidelity optimization in this space. And that is something that hasn't been done yet, but is very interesting. A final speedup technique that applies only to architectural choices and not to other hyperparameters is the area of so-called zero-cost proxies. So a zero-cost proxy aims to predict the performance of an architecture at minimal cost, thus the name zero-cost proxy. And it does so, for example, by executing a single forward pass and a backward pass, and then studying various characteristics. So for example, the gradient of the individual weights. Or it can also study the variety of the outputs that you get from the forward pass from the different elements in the batch. And zero-cost proxies are a very active area of research because, of course, if you can predict the performance of an architecture at basically zero cost, then you can do very fast optimization of architectures using this proxy. So to end this video, I would like to briefly discuss these different speedup techniques with you and put them into perspective. So neural architecture search research really focuses quite strongly on these different directions of one-shot models and lately also zero-cost proxies. However, I would like to emphasize that really both of these types of methods are often quite brittle. So in particular, the DARTS algorithm, for example, often returns these degenerate architectures. Well, for example, we have a paper that shows that for many different types of search spaces, it produces only skip connections. So pretty much the most degenerate architecture you can think of. And likewise, zero-cost proxies actually often don't even outperform trivial baselines. So for example, the number of parameters is a zero-cost proxy because you can compute it at basically zero cost. And this proxy actually correlates very strongly with performance, but that's sort of trivial. Everybody knows that if you make your network bigger, then that often goes hand in hand with getting better performance, but that's actually not super interesting. And so in contrast to this, the HPO methods that we discussed throughout this lecture, which actually also apply to neural architecture search, they are actually typically much more robust, in particular multi-fidelity optimization and prior-based optimization and transfer learning where applicable. So they're very robust and they're getting ever more efficient. So in case of doubt, if you want to use neural architecture search within your work, typically those are good go-to methods, and only if these are really too slow for a particular application at hand, then I would go to look at one-shot methods. Of course, if you want to do research in neural architecture search, then one-shot methods and zero-cost proxies are also very interesting. All right, and that brings us to the end of this video. So as always, I'd like to leave you with some questions to activate the material. This is also the last video of this week, and in fact, the last video of the entire course. So thank you very much for sticking with us until the end. Bye.